Okay, we're recording. Okay, thank you guys for coming. This is our final presentation. It's 25 minutes long. We're going to talk about getting to know our own home's flammability. You all have your packets. In the packets, you have a terms and definitions key with the equations we'll be using, a key for your fire tetrahedron. You have your blank layouts that we'll be using, and then we have our cheat sheets for our furniture weights that we'll use when we're converting our own homes, BTUs. All right. So, oops, sorry. I'm supposed to introduce myself to you guys, even though you all know me. I have been in the fire service for 6 years. I have an Associates of Applied Science in Municipal Fire Control, which is fire science, and then I've had extensive training in understanding and estimating fire loads and how they affect fire behavior. That's a really big portion of being a firefighter, especially in a rural area, when you're working really closely with small communities and trying to make them be as fire safe as they can. So our objectives today are basically we're going to learn how to estimate our own home's fire load. We're going to be using just the living room for an example, but once you've learned the equations and the conversions, you'll be able to apply it anywhere in your home. But we're going to do the living room specifically today because it's pretty easy to draw and sketch out, and the furniture is pretty much the same in most living rooms. We're going to be able to distinguish between natural and synthetic combustibles and their different burning characteristics and burning times. And we're going to be able to identify what certain building aspects and building characteristics contribute to the spread and development of fires. So, in your packets, on that blank form, I want you to take a minute and just sketch in your own living room. I know the shapes aren't all exactly the same. Sketch in where your couches are, coffee tables, TV stands, TVs, whatever you have in your living room. Go ahead and sketch those out. And we're going to use them at the end of the presentation. They don't have to be perfect to scale.
That's not true.
Sean's going to make them perfect, okay. That's all you have in your living room?
I don't have a lot of furniture.
That's okay.
All I have is a beanbag.
Do you have a TV on your TV stand?
Yes.
Do you have a coffee table or end tables with your couch?
Nope.
Okay. No lamps?
No.
Okay.
It's very dark.
No curtains?
No.
Okay.
They're made of plastic.
That's okay. Your living room should be fairly easy to sketch, Dalton. Okay, everyone's got their living room?
Yeah.
All right, go ahead and set those aside. We're turning them over. We're going to use them after we've learned how to convert those pieces of furniture into energy. All right, so that terms and definition sheet, we're going to talk about everything that's on it, but if at any point you guys get confused, you can just refer to that and it's got that information. So we're going to start about talking about the fire tetrahedron. This is the basics of fire, okay? So fire needs 4 things to exist. It used to be 3 things, and it was the fire triangle, but they realized something was missing. So to have a fire, a flame, you have to have heat, oxygen, fuel, and then a chemical chain reaction that brings all 3 of them together. So when we're trying to put out a fire, if we take away any one of these, we don't have fire anymore. So for us as regular homeowners, not firefighters, basically we're talking about fuel, because we can't do anything about heat or oxygen on a day-to-day basis. You know what I mean? We can't control taking all of the heat away from a fire, and we can't eliminate the oxygen in a room. But we can control our fuel. So our fuel in terms of our home is everything we have available to burn. So like in this room, that's our furniture, our carpet, wallpapers, and structural components. Anything that's available to be turned into energy. And when we turn that into energy, we get smoke from our fire. So smoke is basically the unburned fuel. It's the product of combustion that always exists, except in perfect combustion, which is not really applicable to firefighting. You can do that in the lab, but we're not going to do that here. So we have a couple different types of smoke, and we're going to see them outside when we go do our observation. But you can see black, white, brown, and gray. You can kind of see all different forms of that in the picture, and they mean different things. So basically, when we have white smoke, that means it's low on fuel. That means that most of it has been converted. So when we burn like wood, we usually just get white smoke because most of it is being converted to heat. When we get black smoke, that means that it's a lot of fuel in that smoke. It's going to be really, really sooty. So that could mean that it's burning too fast or too hot, and most of it is just being converted into vapors and pushed out to the atmosphere because it's not burning quickly enough. And then gray smoke is right there in between. Brown smoke, we don't really have to talk about because we're not going to encounter it, but it's just basically an oxygen deficient fire. So there's lots of fuel and it's hot enough, but there's not enough oxygen for it to actually convert to flame. The smoke will be different based on what type of combustibles we're burning, and like I said, we'll see that outside. So when we are burning those synthetic combustibles, we're producing toxic gases, and that's why it's a big concern for us as homeowners. So the toxic gases we're producing are hydrogen cyanide, carbon monoxide, hydrogen chloride, ammonia, just to name a couple of them. So most of those we kind of know off the top of our head that are really, really dangerous, right? Hydrogen cyanide, used as poison, probably not the best for us. Burning polyurethane foam yields all of these gases, just burning a piece of polyurethane foam. The couch that we're sitting on right now is polyurethane foam. We're gonna go outside and burn some polyurethane foam. Very few people die in fires from burns. It's almost always from asphyxiation from these toxic gases. Most people, when they die in fires, either it's because they never got out of bed from the carbon monoxide, or they never made it to their door because they came downstairs, breathed in that smoke, and died somewhere along the path to their escape route. Okay, so we have our common versus synthetic combustibles. This is really what we're going to hit on today. So the common combustibles are anything that are made from natural materials. So we have solid wood, cotton, wool, plywood, etc. Natural fibers and natural occurring solids. They ignite slower, they produce less heat, and they burn for longer. That's why they're kind of ideal for burning in our wood stove. Wood takes a while to pyrolyze, and it produces a lot of heat. The synthetic materials are those created by non-natural compounds, so plastic, polyurethane foams, pressed board, OSB, anything that we had to create is going to be a synthetic material, and they're really, really popular because they're really cheap. They ignite quickly, they produce high heat, they burn for short periods of time, and they're really, really volatile when they do burn. The BTU is the basic source of energy that we're converting today. So we're going to be converting our furniture into BTUs. That's basically the amount of energy it takes to raise 1 pound of water at 1 degree Fahrenheit. That really doesn't affect us at the homeowner level, but it makes a big deal when we are talking about firefighting and choosing water streams. So all fuel sources can be estimated in BTUs. We can break everything down into BTUs, which is what we're going to be doing today. So common combustibles yield 7,000 BTUs per pound, and synthetics yield 16,000 BTUs per pound. That's on your cheat sheets on there. It's with your equation because we're going to need it. All right, so we're going to do a couple estimations. So you guys have your calculators on your phones and you have your pens. So I want you guys to calculate what a 200-pound couch made of synthetic material is in BTUs, a 75-pound coffee table made of real wood, and then 2 45-pound end tables, each with 3-pound lamps on them, all made of synthetic material. So when you guys get those, just holler. Grab your calculator. Don't do it in your head. Use your calculator. So I've given you the weights and you have the equations right there in your packets. So we're going to use the number of pounds of the material times the BTUs per pound. Don't get them right, that's okay. Oh, I'm sorry. I forgot I put that one on a timer. There we go. I put that on a timer.
We're slow, it's okay.
Sorry. And this is basically what we're going to be doing at the end with our real living rooms. We're going to be estimating the weights of our furniture and figuring out just how much energy we like to sit on and watch TV. Everyone got it? Yes? Okay. Alrighty. So, as we can see, and we can see from our numbers, really simple things have a lot of energy output. So a basic 3-person couch can put out 3.2 million BTUs. That's a lot of energy when you think about the fact that let's say 1 BTU raises 1 pound of water 1 degree Fahrenheit. So 212 takes a pound of water from sitting to boiling, like from frozen to boiling. Like, that's pretty impressive. And you can see that the wood coffee table puts out less than, or just at 500,000 versus 3.2 million. So you can really see the sharp difference in synthetic materials. The nice heavy coffee table versus the 2 really light end tables, 3 times as many BTUs because it's a synthetic material. All right, so this is our legacy versus our modern living room. Our legacy is like our 1970s living room. Modern is today's living room. I want you guys just to look at them and shout out some differences you see between the two.
Shag carpet.
Shag carpet, okay.
Hardwood. Yeah, a lot more hardwood.
Okay.
Built-in shelving.
All right. How about the material usage?
There's a lot of throw pillows and stuff
Yep.
in the modern living room, so more synthetic materials.
Yep. And let's look at the coffee tables. Probably Rowood coffee table.
Mm-hmm.
Nice light plastics and pressboard, right? Synthetic materials. Same with the lamps and the couches.
Mm-hmm.
That's nice heavy like wool and cotton blend materials. This is all that like microfiber and all that big stuff. So this is just a representation of, this looks like it has a lot less material in it, like physically less poundage, but it is far more energy than was in this, which really affects our escape times. You know, if we think most of us are coming from downstairs or from down the hall, we have to get past all of this energy that's going to burn really, really quickly. Especially if we have to go through our living room. Okay, so we're gonna watch this video. We're gonna kind of skip through it till we get to the important part, but it's a UL study. They built 2 side-by-side burn props. One is a legacy home, one is a modern home. And we're gonna see just how quickly things can change in them. Okay, so as you can see, there's 2 firefighters in each. They basically lit a road flare, a road torch, and set it on the couch in both rooms. So at 45 seconds, there's not a whole lot going on. You can see a little flamage. This is starting to produce some smoke. Nothing too crazy. By a minute and a half, this, oh, do we pause? Sorry. Pause. By a minute and a half, this is already producing those toxic chemicals. You can see the smoke line building up. This is just kind of burning the corner of the couch. It's just burning cotton wool. It's not really producing a lot. This is probably already hundreds of degrees up at that ceiling line. So your smoke detectors are obviously already going off if they're not already melted. You've hopefully, if you had them in the correct places, already been alerted that there's a fire in your home and are working to escape. You can see, I mean, within a minute and a half, that this is already a super dangerous situation. Let's fast forward to about 2.5 minutes.
Wow.
Now our whole couch is on fire, right? And in our legacy, it's still just kind of burning in the corner of the couch. There's still not a whole lot going on. Those synthetic materials reach their flash point very, very quickly. You would already be burned and asphyxiate up at this level if you were to try to walk through it. And by, we'll call it 3 minutes and 30 seconds, you're at a fully involved fire. Every surface in that room has reached its ignition point and is burning. And in the legacy room, we're just now reaching the ceiling with our flames. Just now. So, talking 3.5 minutes to fully involved, everyone in the house is going to die. Okay, that's considerably faster. No, sorry, wrong button. There we go. All right. So I want everyone to think about, what do you have to do before you can get out of your house? Who do you have to grab? You gotta grab your wife, your dogs, your kids, your valuables, anything like that. Think about how much time that would take you if you had to do it in the middle of the night, trying to find your glasses, trying to get some shoes on, or whatever else you had to do. 3.5 minutes goes by really, really quickly. And especially when most of us don't live in our living rooms. We live upstairs, down the hall, you know, so you don't have a lot of time. And that's only if it starts in your living room. If it starts in your bedroom, you have even less time. All right, so we are going to pause our video. We're going to go outside and restart it, and we're going to burn some natural combustibles and synthetic combustibles. So we're going to pause this right here. We're going to pause the video. We're going to go outside.